So we are dealing with diffusions in a, well, eventually we want to consider diffusions in a random environment with drift. Let me write again the equation. So we have a diffusion with a drift part, with a symmetric part. Dwt, this is bare motion plus first drift part dt. So this is a self-adjoint part, right? This b omega is 1/2 div a omega, and then we want to add local drift part of threads lambda, which has this form. So lambda times a times some direction E1 dt. Okay? And A1 is fixed. Lambda eventually will tend to 0. So anyway, I will always choose lambda smaller than 1. And to fix ideas, we'll take for E1 the first coordinate vector, which is not any loss of generality. Just for the drawings. And now, what we saw, in particular last time, is that this process, we got an upper bound on what this process does. So we checked last time that, in a certain sense, x lambda omega 0t. So this 0 is just to indicate that the process starts from 0. So at time 0, we are at 0j. So we check that this process doesn't go too fast. It's smaller than some constant times lambda t. And so we proved things like this in terms of moments, and this is going to be true with high probability if C is large enough. And that is not very difficult, and actually we proved that in a more general case where we can add an additive functional which is in h-1. Not exactly in h-1, in h-1 infinity. And now our next task is to get a lower bound. So we want similar, so we want to prove that indeed that we have the opposite bound, which means that at time t the process does move in the direction E1. Take the scalar product with E1. So we want to prove that this is larger than some constant, a different one, times lambda t. And that, so that we don't expect that to be true for all lambdas and all t's, because that is due to the effect of the local drift. And the local drift is going to take over only when it is stronger than the diffusive part. So we want that in the regime where lambda squared t is larger than 1, say. Okay. So that's what we are. The first thing I want to explain today is how we get this kind of bound. And, okay. So we will rely on one key lemma. That key lemma is a purely PDE statement. It has nothing to do with random environments. It's just for a fixed choice of A omega. So I'm taking some A, which is a diffusion matrix, and I assume that it is smooth, convenience, and uniformly elliptic. And then I'm going to look at the process generated by the operator, the same as above, with lambda equals 1. So I'm looking at the generator L, which is 1/2 dV grad, plus the drift part, which is A dot P1 gradient. And I want to, so the first thing I want to do is to express the fact that the diffusion process associated with this operator tends to go to the, in direction E1, which is rather intuitive. And I want to express that in a way which is rather quantitative. So I will call kappa, as before, the ellipticity constant. And then my statement is about the probability to go to the right rather than going to the left. So for a certain L, which is positive, we look at the exit time from a slab, which I call pi. So pi is a set of x's such that we are in the slab between minus L. So minus L is less than x dot E1, less than L. And I want to look at the exit time. So let us call U of x for the probability to exit to the right. So the probability of exiting this pi from the right side. Okay? So the probability to hit the hyperplane where x dot E1 equals L before hitting the hyperplane where x dot E1 equals minus L. Something wrong?
You start from x.
Starting from x. Okay. And okay. So the statement is about U, which depends on L, of course, but the statement of the lemma, so the claim, is that this probability is going to be bounded away from 1/2, provided that we choose L large enough. So there exists a certain L0 such that for L larger than this L0, then now if we start at 0, so U of the origin is larger than something, say 2/3. Okay? And it's important in that lemma that the length L0 does not depend on anything but the ellipticity constant and the dimension. So L0 depends only on kappa and d. Now, we're going to prove that, and then we will apply this result to these diffusions over there. Now, I didn't record it, but I'm assuming that the coefficients A omega are uniformly elliptic and smooth. And we will apply the key lemma to the rescaled diffusion like last time. So as we did in the last lecture, we rescaled things. So instead of considering the process X, we consider the process with a tilde, Usually the tilde for me denotes the fact that we change space by a factor lambda and time by a factor lambda square. So we just look at the rescale process on this time space scale, and it will work because then if we look at the generator of this guy, L tilde, it is indeed of the form 1/2 div A omega computed at point x over lambda, and then the gradient plus, and then we scale the lambda out of this equation. So we only have A omega at time at point dot over lambda dot E1 and the gradient in the new coordinates. Okay? So we have fast oscillating coefficients, but we don't care because the lemma says that we have this estimate of exiting from the right uniformly in terms. I mean, L0 only depends on kappa, and kappa doesn't depend on lambda. So it's quite important that L0 does not depend on anything but the ellipticity constant, but this will be sufficient for our purposes. Okay. So, so I did my best to keep my promise that the first 2 lectures would be introductory, and then I said that the third one would be more technical. So here is the technical part. Now I will spend some time just proving that that lemma, which once again is a purely deterministic and purely PDE lemma, which is absolutely intuitive that if you have a drift in direction E1, then you should have a bigger chance to exit from the right than exiting from the left. But I don't have 2 lines proof of that. So it will take a little bit more than 2 lines. Okay, now, so the proof of this key lemma. By the way, if you have a simple proof of this lemma, you're welcome. Just to fix the notation, so E1 is the vector in the first direction. A point x in Rd, we will write it as x1, x bar, where x1 is the first coordinate, and x bar is the rest. And x bar is in Rd minus 1. Okay, now the proof uses, what does it use? So first it uses the fact that it uses energy estimates. So we're going to use the fact that U is a harmonic function in pi. So U is harmonic in this domain pi. And so by the way, in terms of notation, there is this domain pi, which is just a slab, and then there will be other domains called pi 0, pi 1, etc. I think that this pi stands for Piatnitsky. So this is a Russian letter, a Cyrillic letter. The proof I'm going to reproduce is a proof in the paper with Nina Gantert and Andrei Piatnitsky. Now, U is harmonic in pi, so it minimizes the energy. So let us introduce some notations. If I have a nice set in pi, I will use the notation E of some function V on G to denote the integral over G of the energy, which is exponential x1 times A of x times the gradient of V squared dx. So from the fact that U is harmonic, we then get that this energy of U and G is the minimum of all energies of V's on G. where V is any function which agrees with U on the boundary. So V on the boundary of G should coincide with U. And, so, and the whole proof is based on that. And now we will apply that to subsets of pi of the form minus LL cross some subset G prime. G prime is a subset of RD minus 1. And then in that case, we have 4 parts, 3 parts in the boundary. There is 1 part at minus L, 1 part at L, and then something from the boundary of G prime. But as far as minus L and L are concerned, then the boundary conditions are easy because U of minus L x bar is 0, and U of plus L x bar is 1. So, let me first outline the argument in dimension 1. In dimension 1, it's quite straightforward. So, we actually in dimension 1, there are many ways to see that the key lemma holds, but here is one way. So, first assume that it's not true. So, assume that U of 0 is less than 2/3. So we get some contradiction when L is large enough by looking at this formula over there. So first, the energy of U cannot be too small because we can write that. So look at 1 minus U of 0. U of 0 is less than 1/3, so than 2/3. So this is more than 1/3. Now this is the value at L of U. So this is the integral from 0 to L of U prime of x1 dx1. Now by Cauchy-Schwarz, this is less than the square root of L times the square root of the integral from 0 to L of the square, U prime of x1 square dx1. And this is less than square root of L times the square root of the integral from 0 to L of exponential x1, because exponential x1 is larger than 1, times, okay, same thing, U prime of x1 squared dx1. And now we have an energy. So this is less than the square root of L times the square root of, let's say, the energy of U. And then I can put the integral from minus L to 0 and add it. It will remain true. So I can put the energy of U on the whole slab pi. So we have a lower bound for this E. And now we can use variation formula over there. So we want to minimize. Say that this is less than E of some function, U bar on pi. We have to choose U bar in a clever way. So what we choose is U bar of X or X1. We choose it to be, so it has to start at 0. So we choose it to be 1 if X is close to, is far away from minus L. So from minus L plus 1 to L. And in between, we have to go from 0 to 1. So we can just choose something like X plus L. Yeah, that's correct. So from minus L to minus L plus 1. Okay, so we have minus L, L. And this is minus L plus 1. And so we go like this, and then it's constant. Okay, and then in the gradient of this function, so everything after minus L plus 1 does not contribute, the gradient vanishes. So the only thing which is left is something here, which then the gradient is 1, I guess. And then x1 is of order minus L, so you see that this is almost, well, this is smaller than something times exponential minus L. Okay, so if we put things together, we see that we have something like L exponential minus L should be larger than 1/9. And so if we choose L large enough, then we get a contradiction, and then U of 0 is larger than 2/3. Okay. Now, we try to adapt this argument when the dimension is larger than 2, larger or equal than 2.
Yeah, I think in the upper bound, some constant. I think kappa should appear in the upper bound.
Yeah. Certainly, you're right. Okay. So I'll put some C here. Okay. So there will be constants. So there are constants that depend only on the elliptic constant, which I may neglect.
Okay.
And also, I will. So in the argument, I may put some constant whose value might change from line to line. And I will treat as a constant something that depends only on the dimension and on the elliptic constant. And also, I will forget lower order terms. So when I have something like L exponential minus L, I will treat it as exponential minus L. Okay. So we try to reproduce this argument in dimension higher than 1. Now, the first part, so we're going to reach some contradiction, assuming that U of 0 is larger than 2/3. So let's assume U of 0 is larger than 2/3, is less than 2/3. Okay. Now, the first argument is okay, almost okay, but we need to fatten a little bit the thing. So the first observation is that if U of 0 is less than 2/3, then U is still less than 2/3 on a certain neighborhood of 0. And that relies on some Harnack inequality. So we use Harnack to say that, say, U of x is going to be less than something, maybe not 2/3, maybe we have to lower a little bit. So maybe 3/5, I don't know. On a certain neighborhood. Of the origin. And once we have this, we can just repeat the argument which is there. And then we get a lower bound. So we get a certain constant such that, the energy of U on pi will be larger than this constant. And the constant does not depend too much on L. So this is the first part, if you want. And then we want to get a contradiction. So actually what we will do is get a contradiction by proving that this energy or some energy, I mean, it's not, you don't have to take pi here. You can take something which is much smaller. So maybe here we can put something which is of the form, say, minus LL. And just to fix the ideas, let us decide that this neighborhood is square minus 1, 1 to the d minus 1. Okay? So just along one line, neighborhood of fixed size along the line that goes to minus L to L. And then we'll get a contradiction by proving that this energy, when L grows, goes to 0 quite fast. And more precisely, we will prove that if you look at the energy of U in a set like this, minus L cross a box. Now, if I want to, okay, so if I'm not mistaken with my computation, the set we will arrive at as this form, minus 2 to the power minus 2d times exponential L over d, and 2 to the power 2d exponential L over d. Okay? So what we will show is that if you take the energy of U in such a domain, then this decays to 0 quite fast. So this is less than some constant times exponential minus L to z divided by d. And once again, in the constant, there might be some lower order terms. So once we have this kind of upper estimate, it's in contradiction with this. And then we can choose L0. Okay? Now, okay. And in order to get the upper bound, we will use the same function U bar, but we have to do that taking into account the extra components. So we use this variational formula, and we use some energy estimates. So let me try to do a drawing. So first we start. So anyway, we are always dealing with boxes. Okay. So this is direction E1. This is the axis. And then in the orthogonal direction you have the RD minus 1. And so we start. So somewhere is the origin. We start in a box of side length exponential L to the d. And this box, I call it pi 0. So pi 0 is the box minus LL. So in the box here, the first component is minus L, and here it's L. So cross something like exponential minus exponential L to the d, exponential L to the d, to the d minus 1. And then we'll do some kind of recursion. So we will start with a domain like this, and then we will divide its side length by 2. So then we'll have another domain, a subdomain, like this, subrectangle, where now the side length is divided by 2. It's exponential L to the d divided by 2. And this subdomain, call it pi 1. So pi 1 is also minus LL. But now cross minus 1/2 exponential L to the d, 1/2 exponential L to the d minus 1. And then you keep going by dividing the length by 2 each time. So you define pi 2, etc., down to pi 2d. And we stop after 2d times because this will be sufficient. Okay? Okay, so now I'm writing that if I look at the energy of U on the big box, pi 0, then this is the minimum of the energy of any function, say function nu0 on the big box, where nu0 should agree on the boundary of pi 0 with u. Okay. So we have to choose this function nu0 a bit like we did here. Okay, I should not have erased because, okay. So inside pi 1, we choose, so nu0 of x equals something. Now, in pi 1, we can choose whatever we want, which is any function which is 0 here and 1 here. So we choose the same as before. So if x belongs to pi 1, then we can choose the function which I just erased. So this u bar of the first component. So u bar is that function that between minus L and minus L plus 1 increases with speed with slope 1, and then it's constant equal to 1. This is u bar. Okay? In between pi 1 and pi 0, we should do something in such a way that we meet the right boundary condition here and also up there. So we do some interpolation between u and u bar. Of x. This is if x is in pi 0 minus pi 1. And now d0 has to move from 0 to 1. So d0 is something like, so d0 of x should be 1. It should be 1 on the boundary of pi 1. So the boundary of pi 1, okay. I mean, on this part, right? So on the set of the boundary of pi 1 intersected with the set where x1 is different from minus L and x1 is different from L. And it should be 0 on the part of the boundary of pi 0, which is down there, and the other one up there. So also on the boundary of pi 0, but the part of it where x1 is different from plus and minus L. Okay? And then you take something linear in between. So d0 has to go from the value 0 to the value 1 in when moving from this to this, and the distance between these two things is exponential L to the d divided by 2. So the gradient of d0 is of order exponential minus L to the d with a factor 2, but we don't have to take that into account. Okay. Now we should compute the energy of this function, nu0. So we use the fact that the energy of u on pi 0 is less than the energy of nu0 on pi 0, and then we compute this one. Oh, what we actually need is just an upper bound. So you take the gradient of nu0 and you integrate it over pi 0. This thing is the integral over pi 0 of exponential x1 a of x, the square of the gradient of nu0 dx. And then there are different things that appear. Now, there is an integral over pi 1. But in pi 1, we only have u bar. So when we restrict the integral to pi 1, we just get the energy of u bar in pi 1. That will not be the difficult part because u bar is explicit enough and its energy can be easily bounded. Then we have to look at what happens in pi 0 minus pi 1. And then we have different terms. So we have to apply the gradient to this expression. Now, if you apply the gradient to u here, you get something which will give the energy of u in pi 0 minus pi 1. So the second term is the energy of u in pi 0 minus pi 1. And I'm just using the fact that 1 minus d0 is less than 1. Then I can apply the gradient to u bar, and I get similar thing when u is replaced by u bar. So I get the energy of u bar on pi 0 minus pi 1. Okay? And then there are other terms which come from applying the gradient to d0. So when you apply the gradient to d0, you can use this bound on the fact that the gradient, the derivative of d0, is of order exponential minus L to the d. So in the rest, here we get some exponential minus L to the d times something. Let's call it I. And this something will involve u and u bar, actually the difference between the two. Some L2 norm of u and some, actually the L2 norm of u minus u bar. But we'll look at that later. Now we can put that term and that term together and put that term on the other side. So we'll get that the energy of u on pi 0, but then we take pi 0 minus pi 1 away, so we get the energy of u on pi 1 is less than the energy of u bar on pi 0 plus something which has this exponential term and this I. So now I need to estimate this I term. So, but basically, not exactly, but I is something like the integral over pi 0 minus pi 1, something like exponential x1, and then probably u minus u bar squared, something like this. Which we can separate the part where we have u bar, which is not very difficult. So let's write this as being smaller than the exponential of x1 times 1 minus u bar plus the integral over pi 0 minus pi 1 exponential x1 times 1 minus u squared. So probably there is a 4 over there. Okay, so that one is easy. And we have to estimate, give some kind of a priori estimate on that one. Now we do the same thing as in dimension 1. So to estimate this term, we just remember that u equals 1 on the set where x1 equals L. So when we look at 1 minus u of x, let's say square. So this is the integral from x1 to L of the derivative. So d over dx, so y1 x bar dy1 square. And then you put the square inside, you make an upper bound with a gradient, and you get that this is less than something. Maybe there is L. In my notes, there are two L's times the integral from x1 to L of the gradient of u computed at point y1 x bar squared dy1. Okay, and maybe I should put A inside, or maybe I should not. But it doesn't mind. I mean, if we want to put A inside this expression, it's okay. So this is a pointwise estimate, and we can integrate this estimate in order to get an upper bound on I. So this I, it will be less or equal than, and then we, maybe not I, but let's say the second part, the part which is the integral over pi 0 minus pi 1 exponential x1 times 1 minus u squared. This we can bound by something like the integral pi 0 minus pi 1 exponential x1, 1 minus u, which is this. So I have 2L, I guess. And then the integral from x1 to L of the gradient squared dy1. Okay. Okay. And this is not exactly what we want, because what we want is to have the exponential term here. We also want A, but A is not difficult to put in. Actually, we can put the exponential term here because we're just going to use the fact that exponential y1 is larger than exponential x1. Okay, and so obviously this is less than the integral of the same thing. So there was the dx1 here, dx1, and then the integral from x1 to L exponential y1 times the gradient. And then we can exchange the order of the two integrals. That will add some L, I think 2L. So maybe we have 4L squared. And then we get the integral over pi 0 minus pi 1 well, actually, it's dx. Then I can put A of x if I want. Then I have to divide by kappa times gradient of u point x squared dx. Yeah, that looks okay. Okay. So if I go back here, you can use this bound. So this is what we get here is, so the constant times the energy of u on pi 0 minus pi 1, but we can bound it by the energy of u on pi 0. So the conclusion of all this, I mean, combining this bound with this thing. Now, we have to estimate the energy of u bar on pi 0, but we also have to estimate this term over there, the first term over there, which has a u bar. But this is very simple, because u bar is localized where x1 is minus L. And then we have this weight exponential x1, which is of order exponential minus L. So all the terms like this one, they are lower than exponential minus L to the d. And so, and then the conclusion is, let me write here, is that we have a bound on the energy of u on pi 1. And this will be less than, let us put exponential minus L to the d in factor, and then there are terms of this order. I get 1 plus the energy of u in pi 0. So what we get at the end is an inequality of this form. And I'm neglecting some lower order terms here, and I'm certainly neglecting a constant. Yes?
The last line there, it's an exponential term missing the integral.
Yes. I changed the notation. Here I was integrating with respect to y1 and x bar, and then I changed the notation. So the y1 has become an x1. But that should be an exponential term, yes. Thanks. Okay. Okay. Now what we do is just repeat this computation. So here we went from pi 0 to pi 1, and then we have a bound with this exponential term. So now we repeat the same computation, but we start from pi 1, and then we divide pi 1 into, we do the same drawing, so we divide the length by 2. So now the length is going to be exponential L to the d divided by 4. And then we go to that domain by 2. And then we keep going this way. So each time we do something like that, we gain one factor, exponential minus L to the d. So you do that 2d times. So what you do is you repeat the argument 2d times in order to get something of the form that, so the energy of U on the domain that you get after dividing the length by 2d times will be smaller than some constant, which is a bit different from the previous one, but doesn't mind. Exponential minus L over d, 2d times, so minus 2L. And then we still have something like 1 plus the energy of U on pi 0. Okay? And then, okay, and in order to complete, we need an a priori estimate on that, but we do something which is very rough, because we just say that, we bound the gradient in L2 by a constant. U is in between 0 and 1. So we can use very easy, very rough bound on E of U pi 0 using just the volume of pi 0. The volume computed with respect to the function which has an exponential growth. So what we have in the orthogonal direction is exponential L to the d to the power d minus 1. And what we have in the x1 direction is exponential L. Okay? So that's exponential 2L minus L over d. So if you insert this bound in here, then you get something which is smaller than a constant times exponential minus L to the d. Okay. And so that's the end of the proof of this key lemma. So I gave the proof. I skipped some of the values of the numerical constants. But the proof, I mean, it should be clear from the argument that only the ellipticity constant enters into the constants. And another thing is that, okay, the reason why I gave the proof is that if you wanted to extend this argument to other models, then you can read from the proof what kind of assumption you need. So, for instance, the way the argument is written, there is, so here we are using the case where we are imposing a constant force in direction E1, and this is the reason why the exponential weight has this simple form, and the fact that the weight which is in the energy has this simple form plays a role, for instance, in this estimate where we really use the fact that the force always pushes in the same direction, actually. So, I mean, what kind of flexibility you get in that proof, you can, in particular, read in this part of the argument. Okay.
Excuse me, I'm afraid I missed the last part of the argument. In the first part, you
This part?
argue about noise in the line below.
This one?
You used the gradient of U is bounded, or you use some under this function?
No, you can use some ellipticity estimate telling you that in any domain of given size, of size 1, if you want, then the integral of grad U in L2, the integral of grad U square, is bounded by a constant times the integral of U square. Just by using the uniformitity on a domain of fixed size, okay? And then you sum up all these estimates. That is, you divide the box pi 0 into boxes of size 1, and then on each one you have a uniformitity or I mean whatever you want to call it, estimate, and then you sum these things. So you have to count how many boxes you have, and in the orthogonal direction you have you just sum the volumes of the boxes, which gives that term, and then you have an extra exponential L coming from the fact that with the way we measure the energy here as this exponential x1 weight. Okay, so that that's quite crude.
Yeah, I understand.
Actually, I'm sure you do. Okay. Is it okay? For I mean, for the others. So. Maybe just I was going to say that I'm going, yes. Okay, so if you allow me to postpone the break, then I will just add some of the consequences of this key lemma. Because this is not going to take long. And this is quite standard. So we apply this key lemma to the diffusion x tilde and also to x. Now, let me, so we apply it to x tilde and then we translate the result in the scale x. So let me write TL, let's say plus or minus L, to be the heating time of the hyperplanes on the right and on the left by x. So this is the heating time of the hyperplane x dot E1 equals plus or minus L by x. And so a first consequence of the lemma is that the probability that you hit the hyperplane minus L, so that T minus L is finite, this decays exponentially fast. So this is less than some constant, C1, I guess, or C. Right? It has an exponential decay. Now, if you do it on the scale of x tilde, then you get an exponential decay in terms of L. But then when you move back to the original scale, you get an exponential decay in terms of lambda L. Okay? And that's easy because you can compare the process x tilde with the random walk which has a bias. So you use the key lemma to couple the process x tilde with random walk which does something like that. Is it jumps of length L0, plus L0 with probability to third, and then it jumps in the other direction, a jump of length minus L0 with probability 1/3, and this kind of estimate is straightforward for random walk. So that is first lemma, lemma 1. Okay. And since I put a small constant here, this is true for all L, for all lambda which is less than 1, and here C and kappa 1, they don't depend on lambda. And that's one piece of information. And then there is another piece of information that we can extract from the key lemma. Okay. This is just about whether we are going to move in the right or left direction. But we need a little bit more. We need to know that we are indeed going to move at some constant speed. So we need some estimate on the probability that TL is larger than the time t. Okay? And that will follow from, so in the proof, the ingredients are this key lemma, plus a little bit of control on the time it takes to exit a box. So actually what we need is just the fact that we need a lower bound on the probability that at time 1, we need something local. So say the lower bound on the probability that at time 1, the process x tilde, so at time 1, is not in the slab anymore. So let's say this is larger than L0. So the key lemma provides the L0, and then we need to know that this is bounded away from 0. Okay? So by time 1, you have a certain probability of leaving the slab, and then you are more likely to leave it from the right, and then you iterate this, or you make another coupling with a random walk with a bias. So the key lemma is okay, and then this is just a local estimate. So that follows from Aronson estimate. And then you get a bound on this probability, which is the one that you would get for a random walk with a bias. So this is going to be less than maybe some constant, exponential minus some other constant kappa 2 times time. But, okay, so this is time 1 for x tilde, which is time 1 for x tilde is something like time 1 over lambda square for t. So here I should have lambda square t. And maybe plus, so did I put another constant? No. Lambda L. Okay, and also because I put a C, then this is okay for all L, for all T, and also for all lambdas less than 1. But in fact, this bound is only useful when lambda squared T is larger than lambda L. But it should be always true. Okay? So the two lemmata here, they express in a quantitative way the fact that the diffusion is going to move in the direction E1, which is what we will have expected anyway. Well, okay. So now I'm going to stop for a short break, but at that point, I'm done with everything I wanted to say in terms of getting a priori estimates on the way the diffusion behaves. So if I summarize what we have so far, we have these two lemmata which express the fact that the diffusion is indeed going to drift in the direction E1. And then from the previous lectures, we had these upper bounds. So in terms of x, we had the fact that x lambda omega 0 at time t is bounded by something like c lambda t. And we had an extension to additive functionals corresponding to functions in h-1 infinity. So the information we have so far is what is said in these two lemmata, plus the fact that if we have a steady state, then it will always be Lipschitz on this space. With the tilde. Okay? And that are things that we can say. I mean, all the estimates are quenched. So this is all we can say. I mean, at least all I can say as far as quenched PD estimates are concerned. And then in the second part of the lecture, we will move to to the next questions. Okay. Any question? Someone? Yeah? Okay. So, 3 minutes break. Yes. I was trying to see that I don't see. 全くわからない先生はあっちですか。あ、そうです。This thing works. Okay, so let's start. Okay. So, make a to-do list. So if we want to complete the program about steady states, fluctuation, dissipation, relations, etc. So there are a few things that are going to be done. One is proof that there are steady states. So there is a problem about the existence of steady states. You remember the question? And then provided we can construct steady states, we can ask about whether we have this fluctuation-dissipation theorem or relations, which would allow us to express the derivative of the steady state on a certain function as some correlation. So, an expression like that, where this is something we discussed in the first lecture. This is some kind of, well, this is some correlation operator. And another thing we discussed is the fact that we cannot hope for a formula like this, at least the way we review it, unless we assume that F is in H-1, and in fact, we don't know how to deal with the full H-1 space, so we'll deal with the subspace H-1 infinity tilde. So maybe just in one line. So when I say that F is in H-1, this means that F is a divergence of something which is in L2. So everything is on omega space. And F being in H-1 infinity, this means that F is a divergence of something which is in L infinity. And the tilde is here to indicate that this big F is continuous. So if I add the tilde, I add the condition that big F is continuous. Okay. So under my standing assumptions, so the assumptions are uniform ellipticity and regularity of the coefficients, plus the assumption that the environment is stationary, ergodic. Then the quick answer to these two questions is we don't know. And I really don't know, I mean, okay, I don't think anybody has any idea about how to get a steady state, for instance. So as far as I know, the best we can do is not to compute the derivative of nu lambda, but just the proof that I gave that nu lambda, if it exists, is Lipschitz continuous. So the situation in which we can answer this question is under one extra assumption about the finite range of correlation. So from now on, I will assume that. We assume, so the law of the environment this Q has a finite range of correlation. R0. So this means the following thing. Let's write H F for the sigma field generated by the environment in a certain set F. So F is a subset of RD. So the environment generated by the random variable sigma omega of x, where x is in F. And by finite range of correlation, I mean that, so this will be the fourth assumption, right? F4. So we mean that if we have two sets F and G such that the distance between F and G is larger than this range R0, then the two sigma fields are independent. Then HF and HG are independent.
Every subset of RD.
Yes, of course. Thank you. So F and G are subsets of RD separated by a distance larger than R0, implies that the environment in F and the environment in G are independent. Now, if we assume that, then we can answer the questions. So assuming A1, A2, A3, and A4, then we have steady states, and we can also take the derivative, which is something that mixes results from the two papers. So the one with Nina Gantert and Andrei Piatinsky, and the more recent preprint of Andrei and I. Concretely, what we prove are the following statements. So we prove, because in the proofs, before I write that, so when we construct a steady state, in whichever sense you mean, we don't, so the reason why I'm assuming here that big F is continuous is because then a continuous function can be approximated by a local function. So concretely what we do is we work with local functions. So just to have a definition, so a function defined on omega, I call it local if it is measurable with respect to the environment in a finite set. So with respect to the sigma field generated by the environment in a ball of some radius R, which depends on F. Sorry. Okay. So RF will be the range of the dependency range of the function F. And so from a concrete point of view, what we are going to prove is that there is a steady state. And in order to do that, we will first prove a law of large numbers when F is local. So there are three statements. Theorem one is about, you want to construct an invariant probability measure for the environment. So you look at something like this, 1 over t, the integral from 0 to t, f of omega lambda over s, which is the environment seen from the particle, ds, and you want to compute the limit of that. So claim this converges. And then when it converges, I write nu lambda of f for the limit. This is an almost sure convergence with respect to everything. So almost sure with respect to q and p. And this is true whenever f is local and bounded. Now, once you prove that, then it's not difficult to extend nu lambda to probability measure on omega. and then you have a steady state in the sense of the first definition. So this implies, so first here, nu lambda is a probability measure, a Borel probability measure on omega, and then nu lambda is the steady state in the first definition I had, definition 1. Okay. So that's the first statement. Then there is another statement which is the same thing, but instead of dealing with functions, we deal with elements in H-1. So let's write it. Theorem 2, same thing. 1 over t, the integral from 0 to t f of omega lambda of s ds converges to something. And then I write nu lambda again. So nu lambda of f for the limit. This is also an almost sure convergence, or L1, as you want. But anyway, it's almost sure L1 with respect to Q. It's almost sure with respect to Q. And maybe almost sure L1 with respect to P, that doesn't matter. And now, whenever F is in H minus 1, infinity, and local. And once again, when you prove that, once you have proved that for a local function, then you can almost automatically extend this to H minus 1 tilde infinity by some continuity argument. And then u lambda will be a linear function on H minus 1 tilde. So here, now, u lambda is a continuous linear functional on H minus 1 infinity tilde. And that gives a steady state. So nu lambda is a steady state. In the sense of definition 2. Okay. And then there is a third statement, that's theorem 3, which says that we have this fluctuation-dissipation relations. So, namely, you can compute the derivative of nu lambda at 0, and this can be done. So, we would like to do it on h tilde minus 1 infinity, but in fact, it's sufficient to do it for local functions again. So, I'm not even sure the way I wrote this thing, but okay, let me write the statement. So, I'm writing the statements the way they are proved, and the way it's proved is for an f which is in h minus 1 infinity and local. So like here. And then, so the statement is the fact that 1 over lambda, nu lambda of f converges to this gamma bar of f that it should be. But again, once you prove that for local functions, you extend to continuous functions, and that's not difficult because we have a priori bounds on this thing coming from the Lipschitz continuity of nu lambda. So this is what we are going to prove, but from that it will follow that the same is true on h minus 1 infinity with a tilde, and for that you use Lipschitz continuity of nu lambda, which we already discussed. Okay. Now, so these are the results from this paper. So how do we prove that? So let me outline the strategy that we use in order to get all the three statements. So the important tool to prove all these things are regeneration times. So in particular, theorem 1 and theorem 2, they follow from the existence and some a priori bounds on the regeneration times and the law of large numbers for RID random variables. So what regeneration times are? So first, maybe I should say, in order to construct regeneration times, we have to move to the path space. So we construct regeneration times on path space. So let me just put a little bit of notation. So I'm going to use this letter, P lambda, with this double P. So usually like this, sometimes with an X to indicate the starting point. So this is the probability measure on path space, and more precisely, this is going to be a probability measure on omega times the space of continuous trajectories from 0 infinity to RD. And at some point it will be RD plus 1. So you will forgive me if I use the same letter. And by definition, the probability of a subset of this is the integral over dq of omega times the integral over the law of the diffusion. So starting at x with the drift lambda in the environment omega of the dp, the trajectory w on A. So if what is first is omega. Omega w belongs to A. Something like this. Okay. So this is what people call the unit measure. So we construct regeneration times. Regeneration times are a sequence of, we construct a sequence of times. Now these times, they depend on lambda. So we construct a sequence of times which is increasing. So the first one is tau 1 lambda, and then tau 2 lambda, etc. Now the first thing is to get these times with the property that if you look at the increments of x, you get an IID sequence. So such times, such that if you look at x at time tau k plus 1, lambda minus x at time tau k lambda, and probably we also need the increments of the times. So tau lambda k plus 1 minus tau lambda k, tau k lambda. These random variables are ID. And P lambda. So here I am only considering the diffusion, and I am on path space, and I'm using x as the coordinate process. So the xt is a path in the space of trajectories with values in RD. So now I don't use the superscripts lambda or omega because the lambda is hidden in the measure itself. Okay? So when you have something like this plus some bounds on these random variables and also this one, then you get a law of large number. So that gives a law of large number for the process sampled as at these regeneration times, and then from that you move to a true law of large number, namely that 1 over t x lambda omega 0 of t converges to something which is deterministic, which is the drift. Now, in fact, this is very good, but this is not exactly what we want when we want to deal with additive functions like this. So we'll have to modify a little bit the construction. And in fact, what we did is we constructed a sequence of times, which are regeneration times. So in fact, we construct these times, to 1 lambda. So I'm using the same notation, etc. But we want to take into account additive functions like this. And in order to do that, so we start with a function f, which satisfies the assumptions of one of the theorems. So I should have said before that you fix an f and you construct regeneration times, which are good regeneration times for the process x plus the extra component that we already considered in a previous lecture. So now I'm working on path space, and I'm going to use the notation z. Now, time is in parentheses everywhere, like here. I'm sorry about that. And this is also, this should be x of t. So now I'm using zt for a path with values in the space of continuous trajectories, but now with values in RD plus 1. And I'm still going to use the same notation p lambda, but okay, so there should be something like this. But now p lambda x will be constructed from the law of the process z lambda omega 0 or x dot, where I recall that this process by definition is, so the first components are just the components given by x, and here we add the additive functional, so the integral from 0 to t f of omega lambda of s ds, plus some extra Bernoulli motion that we just put here for convenience. Okay? So same construction as before, but you add an extra component in order to include the additive function. So in order to get the statements of lemma of theorems 1 and 2, rather than constructing a sequence of times for which we have this IID property for x, we construct a sequence of times for which we will have the same property for z. So we'll have that if you look at z at time tau lambda k plus 1 minus z at time tau lambda k, and also the increments of the times themselves. These are IID. And that gives the law of large numbers for the last component in z, which is the additive functional, and then there is a noise, but the noise doesn't contribute. So this leads to the law of large number for the additive functional, for the integral from 0 to t of f of omega lambda over s ds, which, depending on the assumptions you put on f, can give either theorem 1 or theorem 2. So we get theorem 1 and theorem 2 by constructing such regeneration times. Observe that when we do something like that, in the construction of the regeneration times, the function f will play a role. And the role played by the function f in the definition of tau 1 lambda, tau 2 lambda is a little bit hidden, but there is but at the end of the day, these regeneration times will depend on f. So here, I don't indicate what the regeneration times depend on, not everything. I usually indicate that they depend on lambda, but actually tau 1 lambda, tau 2 lambda, etc., they will depend on f. Okay, so this is one way, maybe not the only one, actually not the only one, but this is one way, the way we used in the paper with Andre, to include additive functionals into this regeneration picture. But there is this fact that, strictly speaking, the regeneration times that we are going to construct will depend on f. And that's where the conditions on f, like here, play a role. Okay? Because we need some bounds on the regeneration times. So we need bounds on the regeneration times for two things. First, to fully justify the law of large numbers from the fact that we have RAD, random variables, but that's a problem for a fixed lambda. So we need some bounds. We need some bounds for fixed lambda. This is for theorem 1 and theorem 2. Okay. and these are, so the bounds that we get is, you fix lambda, you fix f also in this second case, and then we have finite exponential moments. For a fixed lambda. So this will come with the construction. And that's one thing we need. And then another thing that we need, and this is for theorem 3. So in theorem 3, we let lambda tend to 0, so we need bounds on the regeneration times that take into account the way the regeneration times are going to change when lambda goes to 0. So we need bounds for lambda tending to 0. And then we can also prove finite exponential moments. But the precise bound that we get is as follows. So let f be a local function in h-1 infinity, then there exists some constants, C1 of f, C bar of f, which are such that we have bounds for exponential moments. So if I look at the expectation, is lambda, of exponential. Now, if I want to consider the regeneration times themselves, I have to put them on the right scale. So the right scale is time is multiplied by lambda square. So I have one constant, C1, of f, lambda square times tau 1 lambda. Okay? And this is uniformly bounded in lambda, so this is less than C bar of f. Okay. And we also need some bounds on the increments of this process. So I'm going to state them in a way which is very convenient. I will also have exponential moments. Now I can take the max. No, now once again I have to put the estimates on the right scale, which means that space is multiplied by lambda. So there is a lambda, and then there is the maximum for s less or equal than tau 1 lambda of z of s. Okay, and then this is uniformly bounded by some constant that does not depend on lambda anymore. Okay, so these estimates Okay, so once again, you prove that for a fixed lambda you have finite exponential moments, whatever, and then you get the law of large numbers, and then you get theorem 1, theorem 2. But then when you want to go to theorem 3, then you need some control when lambda tends to 0, and this is more than sufficient. And, then, and at some point in a forthcoming lecture, I will explain why and how this is, why this is more than sufficient. Okay? So, I should give some references. Different things. So, as far as so there are different things. So, one thing is the possibility to construct times, where you have this kind of decorrelation happening. So, actually, some regeneration property. Now, this goes back to, I don't know exactly, to where. At least, I think that there is, in particular, one paper by Kesten where this is used in the case of random walks in random environments in dimension 1. But the construction of regeneration times for different models of random walks in a random environment was very much investigated by Anna Sol-Snitman. So there are many papers by Anna, in particular one with Martin Zerner, where regeneration times are constructed for a model which is a little bit different, but still satisfies property A4 for random walks. So discrete models. And then there are other papers. For instance, there is one paper by Anna Sol in the case of random walks on percolation clusters, etc. So in the case of, and once again, and in these papers, something like theorem 1 is also proved. That is, from regeneration times you get steady states. The precise reference in our case, so the paper dealing with diffusion processes is a paper by Yan Chen. So it was Yan Chen who really wrote the details of the construction of these regeneration times in the case of a diffusion, which is a little bit different from a technical point of view than dealing with discrete random walks. The construction of the regeneration times I'm going to use owes a lot to the construction of Yan Chen, but it's not exactly the same. It's not exactly the same because if you read Yan Chen's paper, adapt it to our context, and then try to follow the computation in order to see what kind of bound you can have on the regeneration time in terms of lambda, you find something which is not good. So if you just take Yan Chen's construction as it is, you find regeneration times which are of order lambda to the minus 3 instead of lambda to the minus 2. So we had to change things a little bit. But the main ideas are already in the paper of Yan Chen. Also, we had to include the additive function, which is not done in Yan Chen's paper. But anyway, about the existence of steady states. So as I said, this you can already read that in the papers of Snitman, and in particular in Snitman and Zerner. There are, so about steady states, there are results about the construction of steady states in papers of Komorowski and Krupa. But I hope the spelling is correct. Now, yeah, it seems to be correct. So I have two references. There are two papers in 2004 and 2006 where the authors investigate to what extent the steady state is absolutely continuous with respect to Q. But they don't actually prove that the steady state is absolutely continuous with respect to Q. They prove that the steady state is absolutely continuous with respect to Q in a restricted sense, on a smaller fluctuation. Anyway. Now, another paper I have to comment a little bit is I erased my own references, okay? So there is a companion paper to these two papers with Nina and Andre, which now it's GGN, so that stands for Gantert, Guo, and Nagel. And what they do in the paper is address the same questions as we are discussing here in the case of discrete models. So they have exactly the same questions, but for discrete models, so for random walks. And they reach more or less the same conclusions, of course, as it should be. So many things. So for instance, all the estimates I explained in the first part of the lecture, you can do them. They actually hold for discrete models, and they are proved in that paper. So the two approaches have many things in common, but as far as FDT is concerned, there is a subtle difference in the statement. So let me give you the statement from Gantert, Guo, and Nagel, maybe. So they construct steady states, and then they prove the, let's say, the fluctuation-dissipation theorem, as we do. So they take the derivative of the steady state, but they prove it when f is local and h-1, and when d is larger or equal than 3. In my notes, I also wrote that f is bounded, but okay. Yeah, certainly f should be bounded. Okay? Mm-hmm. So you see, it's a little bit different from what I stated, because it's actually better, because in my statement, I didn't have the condition h-1, I had h-1 infinity. Okay. It's also worse in the sense that they have to consider the case where d is larger than 3, larger or equal than 3. So actually, this may not be the right way to state the theorem. This is the way they prove it. But if you are in dimension larger or equal than 3, and if you have, as we do, assumption A4, then a local function, which is bounded, is automatically in h-1. So you can erase this condition. When d is larger or equal than 3, then f local, maybe bounded, implies that f is in h-1. And, okay. Now, this is a rather soft argument. It is in Jean-Christophe Morin's thesis. One reason why Gantert, Guo, and Nagel reach a conclusion which is a little bit different from ours is because they put in the machine some quantitative estimates about from homogenization theory. So you see, the first step in that direction is to use this property that local functions are in h-1. So as I said, this is a rather soft argument which relies on the fact that in dimension 3 you are in a transient regime, random walks are transient. But in fact, in order to establish the fluctuation-dissipation theorem, then the proof of Nina, Xiaoqin, and Yan, it uses some more quantitative information about the central limit theorem. So here you use a little bit of quantitative homogenization. So more precisely speaking, they could make the proof with results also from Jean-Christophe's thesis. Now there are many results in quantitative homogenization by many authors, and okay, maybe they could be used in order to prove more quantitative statements than FDT. Why not? But this has not really been done yet. Okay, so at some point there is a difference between the two approaches. In particular, the idea of using regeneration times that depend on F is something that we use with André, that they don't use, but anyway, one way or another, at some point, you have to put some restriction on F, which is of H-1 type. So here it's a little bit hidden because of this property that local functions are automatically in H-1. Okay, so you can discuss the advantages and disadvantages of the two approaches, but what I'm going to do in the rest of the lectures is explain how we, André and I proved this, and also theorem-free, and at least one advantage of this approach is that we don't use quantitative homogenization at all. So the proof is self-contained, if you want. Whatever you do, so I mean, we can discuss whether the results should be true on H-1 or only on H-1 infinity. I don't know, it's an open discussion. One thing which is clear from, for instance, this kind of estimate, if you really want this to hold, then you really have to impose that F is in H-1. You see, this would not be true. If F is not in H-1, then the additive function is going to grow linearly. Tau1 is of order 1 over lambda square. So this term, lambda times this max, this will be of order 1 over lambda if F, let's say, is not in H-1. Now, whether we have to put this infinity here or not, okay, this is something. Okay, it's not 100% clear. Anyway, okay, so it's time to stop. And what remains to be done is discuss in more details the construction of regeneration times. In particular, I want to make explicit how it depends on F. Why does it depend on F? And then from the existence of regeneration times and estimates like this, we will see how one gets fluctuation-dissipation relations and the Einstein relation. So, thank you. I got all the maths. So I leave the microphone in case you have questions.
I think you also need a moment estimate for the difference of two successive regeneration times. It is the statement for the. Is it straightforward from those estimates?
In fact, it will be straightforward. I mean, in the construction of the regeneration times, you can put Tau2 minus Tau1 here. Just Tau2 minus Tau1 will have the same law as Tau1. Condition to something, but condition to an event of probability you have.
Okay.
So I write it like this because okay, it's in our construction of the regeneration times, this turns out to be sufficient. But otherwise, you're right. Indeed.
You have sufficient moment condition, you have low large numbers. But as you said, regeneration time depends on
here, yes.
Yeah. So is it clear you can find the probability measure in lambda which unifies the limit
Yeah.
of low large numbers?
Yes, I mean, not completely clear, and your question is fully justified. So you have to be a little bit careful. So yeah, I was a little bit too quick. So I just wrote finite exponential moments, but these finite exponential moments, they depend on f, and you have to be sure. Okay. Actually, what happens is that these finite exponential moments here so in the case, this is when you want to get theorem 1, and then you have to know more. You have to know that this is uniform with respect to f, let's say with, okay, so if you have a uniform control on the n-infinity norm of f, and also if you know that the range of dependence of f is less than some constant, 1. Okay? So we need more than just, for a fixed f, you have a finite exponential moment, but you can choose the same, you have a uniform bound like here, for all f's with a fixed support and with a fixed n-infinity norm. And once we have that, then we can. Yeah. Oh, but then it's very elementary because you construct a probability measure on omega with the sigma field of generated by a cylinder, and and you can do that for all cylinders, and then everything is coherent. Okay, yeah. And then you go to the projective limit, which exists, and then it's so once you have this, it's not a big deal. But indeed, you should have something like that. Yeah. And you will see in the construction that this holds.